All right, so please bring along your own writing paper, GC and MF26 or Compass, whatever lah. Right, because we'll be testing advanced drafting techniques. All right, please be punctual. All right, it's at 9 o'clock. Right, so please make your way down quickly after assembly. It's 50 minutes. I think you need all the 50 minutes to answer my questions. All right, so please don't be late lah. All right. Can? All right, so right, if you still remember last lecture, right, I talked about lines in more details, right, after we have done the recap about equation of lines, right, in either vector form or Cartesian form, right, then we talk about the whole idea of giving you equation of lines, right, is to solve questions, right, related to lines. It could be either point line or two lines. Right, so as a quick recap, remember that if it's a point and line, right, if you have a point and line, right, of course you will want to check whether a point is on the line. So once a point is on the line, nothing can be asked. Okay, the one that I'm interested in, right, is when the point is not on the line. Okay, so let's say this point B, right? Remember that in order to pinpoint the line, I must give you a line that passes through point A, right, with direction vector D. So these two things, right, must be given. Right, if not, I cannot solve the equation. I mean, I cannot do anything to it. I need to know a point and a direction vector so as to get the equation of the line. Okay? So if I actually ask you to find the a question related to point and line, of course the first one, if you recall, right, is to find the foot of perpendicular from the point to the line. Okay? So the idea behind, remember, is to make use of the fact that BF is perpendicular to the line, which means BF dot D must be 0, right? And this is the equation that we use, right, to solve for lambda, right? Because bear in mind that OF is actually A plus lambda D, right? Remember that this is the variable that you are supposed to solve when it comes to equation of a line, right? So you have to solve this variable lambda. Right? And so this is the equation for you to solve lambda so that you can find the position vector of the point F. Right? So this is the usual way, the standard procedure to make use of BF dot D equals to 0. Then of course after that, we are also interested to find the shortest distance, isn't it? Right? This is another very common question that we ask you. If the point is not on the line, then I can ask you to find the distance between B to the line. So the trick, of course, is to use dot product or cross product. Now, the idea behind is to then create this vector AB, right? So BF is actually the opposite of this angle here, right? So which means I can then make use of cross product. This is just AB cross D cap. Right? So this will give me the shortest distance. Right? If the question asks you to find projection of AB onto the line, right, so this is the projection, right? So this is just AB dot D cap. Right, if I want to find the length of projection of AB onto the line. Okay, so these are the standard questions when it comes to point and line. Okay, then after that, we talk about what happens if you have two lines. Okay, so for two lines, again, we have some standard scenario. Okay, so it's either they are parallel, right, or intersecting. Right, and the last one, we call them skew lines. Okay, so parallel lines, if I give you two parallel lines, that means that they must share the same direction vector. Right? If not, doesn't make sense. Right? So I need, in order to check whether two lines are parallel, all I need is to check whether they have the same direction vector or parallel direction vector. It may not be the same, but it must be parallel. Okay, so once the direction vectors are parallel, then I know that the two lines are parallel. Of course, we go about checking whether the two lines are the same line or not, right? Usually no lah, but in the event that the two lines are parallel, what can we ask? Right, I can only ask you one thing if they are parallel. Right, that is to find the distance between these two parallel lines. Right, when the two lines are parallel, I cannot ask you a lot of things. I can only ask you for distance. Right, so first I can ask you to establish that these two lines are parallel, then find the distance between the two parallel lines. And it's not hard because I know that the line line L1, right, and L2, right, will have two given points. Right, let's say A is on L1, B is on L2. So in order to find this distance, all I need, once again, right, is to connect A and B, right? And so the distance is just AB cross D cap, right, once again. Right, so essentially it is the same as finding the distance of point B to the line L1. All right? So it's the same idea. Okay, so if two lines are parallel, I will ask you for distance. Now, if two lines are intersecting, right, so then usually they will have a common point, let's call it X. Okay? So of course, I will then ask you to find this point X by equating the two equations. Right, so once you equate the two equations, then you solve for the lambda and mu, right, and make sure it's consistent. Right, again, remember the lingo that we use, you must show that lambda and mu is consistent for all three equations, and simply you can just use your GC to get it. Right, so that's the first thing I can ask you to find the common point. Next, I will ask you to find angle. Right, I can ask you to find angle. So let's say this is L1, this is L2. Right, let's say this is D1, and this is D2. Right, so cosine, right, to find this angle, all I need is to use cosine theta equals to D1 cap dot D2 cap. And because the angle, when it comes to two lines, it could be either the acute angle or the obtuse angle. Typically, we will always ask you to find the acute angle between the two lines. So that's why you have to make sure it's positive for the cosine. Right, so it's just the dot product of the unit direction vectors for L1 and L2. That's it, okay? Now, if it's skew line, I need to go one more page because I have to draw a bigger diagram to let you visualize. Right, anyway, what I'm doing here is all in your notes, right? So I'm just doing a quick summary of what we have done so far. Right, if you remember, when I introduced skew line, right, I mentioned about the two lines are actually on two parallel planes. Okay? You draw, let's say this is L2, right? And then L1. Right, you take it as the two diagonals. Right, the one on the bottom surface and the another one on the upper surface. Right, the two opposite diagonals. Right, so in drawing like this, right, then we are quite certain that L1 and L2 are skew lines, meaning they will never intersect. Right, because the plane is actually infinite dimension. Right, it just extends on and on. This is just a so-called snapshot, right, and making things look nicer. Okay, so with that, let's say this is your D2. And this is your D1, right? Okay, so when it comes to skew line, you will first ask to establish skew lines, which is again just equating the two lines to see whether is there any common point. Right? If the system is inconsistent, then you will have skew lines. All right? So once you establish that they are skew lines, what can I ask you after that? The first thing I can ask you again is angle. Right? Because I can, although they are not intersecting, but I can always shift the line L2 down, right, to this line here. Let's call it L2 prime. Right, so I can just shift the line L2 down so that it intersects L1. And so this is the angle that we are interested in. Right? So even though two lines are not intersecting, I can still find the angle. Alright? I can still find the angle. Alright? So this theta, once again, right? The idea behind is cosine theta is the dot product, right, of the two direction vectors. Again, is the unit direction vectors. Alright? So again, remember, even though the lines are not intersecting, I can still find angle. It's perfectly okay to find angle. Alright? There's one more thing that in tutorial questions, then you'll be exposed a bit more. Right? I can actually ask you to find these 2 points. Right? A very special point P and Q. Right? Such that PQ is perpendicular to L2. PQ is also perpendicular to L1. Sorry, not this one. L1. Right? In your tutorial, you'll be exposed to this. Right? A bit more in this one, we have to guide you to find this point P and Q, right? Such that PQ is perpendicular to L1 and PQ is also perpendicular to L2. The purpose of finding these 2 points is that this will then give you the shortest distance between the 2 lines. Right? If I have 2 skew lines, PQ will provide me the shortest distance between L1 and L2. Alright? So that's a guide. Usually the question will guide you to find P and Q first, then find the shortest distance. And the trick over here is to notice that 90 degrees, right? 90 degree, oh. So the standard trick, what do? Alright, PQ and D1 must be perpendicular. PQ and D2 are also perpendicular, isn't it? So which means I can then use the fact that PQ dot D1 equals to 0. PQ dot D2 is also 0. And I use this, right, to solve lambda and mu. Right, remember L1 will have a lambda, L2 will have a mu. Okay? So this will give me 2 equations, right, to solve for lambda and mu. Okay? Right, in tutorials we will expose you more to that. Right? Okay, so we end off in the last lecture about finding the distance, right, between these 2 lines. In this case, the 2 lines are parallel. Right? If the 2 lines are not parallel, meaning they are skew lines, I have to guide you. Alright? So with that, and as I mentioned earlier, so all you need to do, right, is to use treat it as a point to a line. Alright? So the formula is just AB cross D cap, simply said. Right? And that's how you get a formula. Right? The last thing that I'm going to touch on is when we want to reflect a line in another line. Right? This is what I mean by a line in another coplanar line. Okay? So there are 2 scenarios in this case. First scenario. Okay? There are 2 scenarios in this case. First scenario. This is L1. This is L2. Right? Meaning L1 and L2 are intersecting. Okay? When 2 lines are coplanar, there are actually 2 cases. First case is when the 2 lines are intersecting. Alright? So once I have this, how do I find the reflection? Right? My interest is to find the reflection. Let me call it L2 prime here. So this is the line I'm interested in, L2 prime. So remember, in order to get the equation of the line, I need 2 things. A given point and a direction vector. Correct? So the moment the 2 lines are intersecting, this point X, right, will also be lying on L2 prime. Correct? So that's why your step 1 is to find the common point between L1 and L2. Once you get this point, your first step is done. Next, I need a direction vector of L2 prime. So how do we go about doing it? Remember, this is reflection. So when it comes to reflection, if you recall in the last lecture, we talked about reflecting a point in a line. Correct? In order to reflect a point in a line, I have to use the foot of perpendicular. So the trick now is, L2, right, definitely I have a point B, right? Definitely I must give you a point B on L2, right? So with that, I can first find point F, which is the foot of perpendicular of B onto L1. Then, because it's reflection, B prime, right, must be such that it is a, F will then be the midpoint between B and B prime, right? Then with that, I have the second point on L2 prime. So simply said, the direction vector is just xb prime, isn't it? Then done. Okay, so that's the procedure on how we find the equation of the reflected line. Step 1 is to find the common point between L1 and L2, so that L2 prime will also pass through that point. Right, step 2 is to find the reflection of point B in L1. Right, so that L2 prime will also pass through that point. With 2 points, I can then give you the equation of the line. Simple? I hope. Case 2. This is another case. L1 and L2, right, are just parallel. Right, it's also possible, right? L1 and L2 are parallel. They are also lying on the same plane. Okay, so with how do I get the reflected line L2 prime in L1? This is actually much easier because if L1 and L2 are parallel, they will so-called share the same direction vector, isn't it? So L2 prime must also be parallel, right, to L1 and L2. So the direction vector is already found. So all I need is one more point, right, on L2 prime. So likewise, we do the same trick, right? We find B first, then find the foot of perpendicular, then find B prime using midpoint theorem. Then we are done. Okay? So if they are parallel, you will have one less to do, right? You just need to, if they are not parallel, you have to find the common point, x. When they are parallel, you don't need to do that, right? Because the direction vector is already there. Okay? Right? So this is what, in summary, right? This is what I've been going through the review just now. The alphabets may not be the same, but the idea, right? Remember the idea behind. It is the idea that counts. You don't need to memorize all this. Once you understand the idea, it will just flow to you naturally, I hope. Okay? Right, so let's look at an example. Right, example 30, you have the point A, right? This is your point A, and the line L has this equation. They ask you to find a position vector of the foot of perpendicular from A to L, and hence find a position vector of the reflection of A in L. Right, something quite similar to the earlier examples, right? So I won't go through in key details, right? So I don't think I need to go through all this in review lah. Of course, as a quick recap, remember that the trick is to use the fact that AF and L, right, are perpendicular, so that AF and the direction vector dot product equals to 0, and then we solve for lambda, right? Remember that, right? Your purpose is to solve for lambda, right? That's the whole idea here, right? Then you sub in, you will get OF. To get the reflected point, all I need is to use midpoint theorem because F is the midpoint of AA prime, right? Then with that, we can get OA prime. Okay, so just a quick recap. Next, let B be a point on L with position vector 6, 4, negative 4, right? The question says find the equation of the reflection, right, of line AB, right? They ask you to find the reflection of line AB in L. So L, right, in this case is your so-called mirror line, right? And what we have done so far, if you recall, right, we actually have point A, right? And earlier on, right, we have already found the foot perpendicular, and we proceed, right, to find A prime, which is a reflected point. Now, B is a point on L, and we are now interested in line AB, right? The reflection must be then BA prime, right? So B is already so-called a common point between line AB and L, so you don't need to find it. It's already given to you. So all I need is to then construct, end of story. Right? That's it. Okay, so I hope you see that in this case, I don't need to find a common point because that point B, right, so that is the common point between L and the line AB. Okay, so all I need is to then construct the direction vector, which is just A prime B. Right, so this point over here, right, again, remember that equation of line is not unique. So this point, right, you can either use OA prime or OB. It doesn't really matter. Right, so you can either use OA prime or OB. You will still get the same, it's still the equation of the line. Right, it doesn't really matter which point you choose. Okay? Great, Ken? If you want to draw a diagram, hopefully, is there a diagram here or no? Right, if you want to draw a diagram, right, this is the diagram that you need in order to visualize. Okay, again, I stress that whenever it's vectors, good for you, diagram. Right, so you have to draw a diagram to visualize the question. Right, so it'll be good for you to draw a diagram before you attempt to answer the question. And hopefully using the diagrams, you can then formulate a strategy to solve the question. All right, so this is one of the very standard, one of the very common strategy that we use to solve questions involving vectors. First step is always draw a diagram to visualize the problem. Right, then we propose a plan and then try to solve it. Okay? Right, so with that, this is just a quick summary of what the key things that you need to know when it comes to when it comes to lines. Again, a quick one just now, right, regarding point and lines, right? Given 1 point and a line or given 2 lines. Okay? Next, now we're going to move on to the most exciting section, which is planes, right? If you think lines are not easy enough, I confirm plus chop to you that planes will get even harder. All right? Yeah, let me just double check. This is the last slide. Yep. Okay? This one really needs you to visualize. You have to use your spatial imagination now. And I try to help a bit in the spatial imagination. Ken? And again, I need you to really pay attention to whatever I'm going to talk about now. Right? Because planes are not as easy as lines. Okay. Now, early on, we talked about lines. Okay, line, in a way, I can still talk about a 2D equivalent. Right, I can talk about the Cartesian, the XY plane, right? I can then try to let you try to see how lines, right, are generalized to 3D. Right, when it comes to planes, right, there's no 2D comparison planes, right? I must go direct to 3D. Okay, now, make things simple first lah. Right, remember when we introduced vectors, we talked about 3-dimensional stuff. Right, so we introduced the X, Y, Z axis. Right, X, Y, Z axis are the 3 lines, right? The standard lines that we use to construct the axis. Now, there is then this very nice, hopefully you can try to imagine, right, that this portion here, right, the XY plane, right, the XY plane is what we consider as a plane. Okay? So-called a base. Right? It's like the base of a box. Right? If you imagine you have a box, right? You have the 3 XYZ axes, right? Then the base of the box is actually a plane. Alright? Now, how do we then talk about a plane? Now, any point on this plane, right? You see, just earlier on when you talk about equation of line, the equation of line is to give us the position vector of a point on the line. So likewise, when it comes to planes, the equation of the plane should give me the position vector of a point on the plane. Make sense? Okay? So, in this case, it's quite easy, right? I can straight away say that this is xy 0, right? Because if your point, right, is on the xy plane, z is always 0, isn't it? Okay? So, any point over here, right, can then be written as xy 0, isn't it? Which means OP, right, which is R in that sense, lah. So let me think of it as R. Right, will then just be xy0, which I can write it as x times 100 plus y times 010, isn't it? Okay? Now, what is so special about 100 and 010? Right, 100 is of course I, right? 010 is of course j. Aren't these two the direction vectors of this plane? Are these direction vectors of the plane? Right, remember, if you talk about direction vector of a line, the direction vector must be parallel to the line. So when it comes to plane, the direction vector must of course be parallel to the plane. Right? So, in this case, I, hopefully from the diagram, you can see that I is actually parallel to the plane. Right? J is also parallel to the plane. So I and J can be considered as the direction vectors of the plane. In opposite line, you just need one direction vector. Whereas for plane, right, you need two direction vectors. Right? In order to so-called pinpoint the plane. Right? And there's one more thing I also need to use, which is the point O. Right? It must contain a given point on the plane. Right? Three flat, let me. Testing, testing. Right? Okay? Right? So earlier on, right, as I mentioned, just like lines, right, I need a point and direction vector. Whereas for plane, I need 1 point and 2 direction vectors. Okay? So that's how we extend to planes. Of course, this is a simple case. I'm just looking at the base. Right? But in general, I can have any plane, right? Let's say this is your plane. Usually we use pi, right, to indicate a plane, or P, right? The plane need not pass through the origin, right, definitely. So, which means, right, I will need a point A, right, that is lying on this plane, and I will need 2 direction vectors. Right, let me call it D1 and D2. Okay, there is no need for D1 and D2 to be mutually perpendicular. I need not have that to happen. If they are mutually perpendicular, it's just a nice thing. But I do not need them to be mutually perpendicular. Right? As long as they are not parallel. Right? D1 cannot be parallel to D2. If they are parallel, it's as good as giving you only one direction vector. So that's no use. Okay? So, if I'm interested to find a common point, a general point R on the plane, right? So our objective, right, is of course to find R, right? OR. That's our objective, right? Is to find this position vector of R with reference to the origin O. Okay? So the trick, once again, is to then find OR, right, is just OA plus AR, right? Okay, how then do I get AR? OA is just A, quite simple enough. How do I get AR? I must get AR using the direction vectors. So how do I then get AR? Now, the little trick here is that we can create a parallelogram using D1 and D2, right, as the adjacent sides. Right? We can then create a parallelogram, right? So this side is actually parallel to D2, correct? So this can be treated as mu times of d2, isn't it? It's parallel to d2. So this vector here, right, let me call it C lah. So AC, right, will then be parallel to d2. So it can be written as mu d2. So AB is parallel to d1, right? So it can be written as lambda d1. So which means, finally, OR is just OA plus AR, right? And AR, right? AR is just AB plus AC, right? Right, based on the diagram, because it's a parallelogram, right? So AR is just AB plus AC. So finally, AB is lambda d1, and AC, right, is mu d2. So this will give us the equation of the plane, where lambda and mu, right, are of course any positive real number. So which means in the case of planes, right, lambda and mu are now the variable that you are trying to solve. Right? So different lambda and mu, right, will give you different point on the plane. Right? So to find the location of this point R, right, you have to actually find lambda and mu. So there are two variables to solve. Okay? So this is known as the vector equation of a plane. Alright? Which is quite similar to the equation of a line, right? The only thing that is extra in the sense is this thing. Right? I add in another direction vector so as to create a plane. Right? For lines, I just need one direction vector. For planes, I need two direction vector. So far so good? Well, with that, then we get very upset in a way because lines, I just need to solve one variable, lambda enough, right? So it's quite simple. For planes, I have to solve two variables, lambda and mu, right? Which may make life a bit hard. And worse off, do you think D1 and D2 are unique in the sense? Right, for a line, right, you will only have one direction vector. Right, all direction vectors of the line must be parallel to one another. Correct? So in the case of line, right, it's always one direction vector, essentially. Whereas for planes, if I have two direction vectors, do you think that these two direction vectors are the only two? Right, can I have another pair of direction vector that will still be parallel to the plane? Right, sadly, yes, right? I can have something like this, right? I can have something like, this is D3, for example, and let's say this is D4. Right, D3, D4 is still parallel to the plane, right? So I can still use them, right, as a direction vector. Right, so this equation definitely is not unique, first thing. Second thing, D1, D2 are also not unique up to parallel vectors. Right, I can actually find another pair which is not parallel to D1, D2, which will still describe the same plane. This is something that we don't like because it's not unique. Right, in math, right, we always like two things, existence and uniqueness. Right, sounds cheap lah, huh? Okay, but we want things to be unique. So instead of looking at direction vector, okay, we like to look at something different, not just the direction vector. Direction vector, as I said, is not unique. Now, imagine the stage is a plane, okay? Imagine the stage is a plane, huh? Looks like a plane, right? Just say limited, lah. It's a plane, huh? Consider me as a vector, lah. Right, I'm a vector, lah. I'm walking around the plane, right? I'm still walking, lah. Right, I'm walking around the plane, oh. My direction at this position and at this position, is it still the same? I didn't slant, hopefully I didn't slant. Right, I'm standing upright now. I stand here, I stand upright here. It's still in the same direction, right? I hope. And more importantly, I'm perpendicular to the plane, right? Right, I'm actually perpendicular to the plane. So no matter where I stand, right, as long as I'm perpendicular to the plane, right, I'm actually in the same direction as my previous position, which is actually parallel. And this is something that I like. Because no matter where I stand, no matter where I put that vector, so-called myself as a vector, right? No matter where I am, as long as I'm perpendicular to the plane, right, I'm parallel to my another position. Okay, so there's a technical name for this vector, which you can call me now lah, normal. Okay, all right, I'm normal, right? So I'm the normal to this stage. Okay, I'm the normal, right? Normal always have the idea of perpendicular. Hopefully you remember that. Tangent normal, isn't it? You remember differentiation, right? Tangent normal. Normal is always the perpendicular line, right? So normal always give you the idea of perpendicular in this case, right? So I'm now normal to this plane. Okay? Again, I have to do something funny again. Right, I have to do something a bit funny again. Alright. I have to sit down again. Alright. Okay, now imagine my legs, right, are the direction vector. Okay? D1, D2, right? Okay, let's say imagine D1, D2. Okay? You do the, remember I did the cross product thing, right? D1 cross D2, right? This is n, right? Again, normal, so I'm the normal, right? So D1 here, D2 here, right? D1 cross D2 is the normal. I shift myself. This two direction vector is now not the same as before, right? They're not parallel definitely, right? Maybe like that, D1 cross D2 is still a normal, right? Right? I can shift myself over here, right? D1 cross D2 is still normal, right? So, which means, right, regardless of what are the direction vectors, as long as you do the cross product, it will always give me the normal. Of course, they may not be same in the sense exactly the same, but they must be parallel. All right? So which means instead of looking at direction vector, when it comes to planes, right, I must look at the normal. Okay? So which means with that, we have a different view of things now. Right? We create this point A, right, and this thing R, right? Again, I must have a point on the plane. If not, I cannot do anything. So, remember initially we have D1 and D2, right? So now, instead of looking at D1 and D2, we will then look at the normal, right, which is the cross product, right, of D1 and D2. Right, so n is the cross product of D1 and D2. Okay, that's how we actually get the normal. Right, I mean, if the question is given to you, right, then that's good. If the question there's no normal, I will take the cross product of the two direction vector. Right, so this is the normal n. So let me just put it here, just to let you see. Okay, so the normal is always perpendicular, right, to the plane. So how do we then get AR? I mean OR. Now, isn't AR also a direction vector of the plane? So AR and the normal, if I put it here, right? If I put the normal here, they must also be perpendicular. Right, which means AR dot n has to be 0. Right, because AR is also a direction vector of the plane, right? So AR dot n has to be 0, which then give us R minus A, right? Dot n equals to 0. Right, which will then give us R dot n equals to A dot n, which is a scalar number, we call it D. So this is known as the scalar product form. Right, so this is known as a scalar product form, right, of the equation, which is actually the most useful equation when it comes to plane. Right, in this form, I can then straight away locate the normal. And in planes, right, normal is the one that I use for direction. Right, for lines, I will use direction vector. For planes, I will use normal vector. Right, normal is the vector I need to use when it comes to plane. Okay? Right, then finally, lines also have Cartesian equation, right? So what about planes? Right, planes we do have, we just need to do a little trick. Right, we can write R as x, y, z, right? The general point, right? So this is your general coordinates. All right? Let's say n, right, is ABC. Let's say So recall earlier we have r dot n equals to d, right? So that means x, y, z dot abc, right, is actually d, which then gives us ax plus by plus cz equals to d, right? So this is known as the Cartesian equation. All right, and the Cartesian equation can be easily converted back, right, to the scalar product form. Right, so if I give you a Cartesian equation, you just need to use one step. You can get back to the scalar product form, which is the useful form. Right, this form is always the one I want to use, right, when it comes to planes. Okay, right. So with that, I have covered these three things, right? The first three different forms, right? I won't run through again. Right, so example 31, this is the case when you are given a point. Right, so this is your given point, right? And parallel to the, is it parallel to the vectors, right? So this is your D1, and this is your D2. Okay, so with that, you can straight away write down the equation of the plane. Okay, so just remember that in this case, right, S and T are the so-called variables, right, that you are supposed to solve when it comes to planes. Right, but as I said, this form to me is very not nice, right? I will prefer to use scalar product form, which is very neat, right? And all our methods that I'm going to use later on will be based on scalar product form, right? So in the event that the equation is given in Cartesian or vector form, you will always convert it back to scalar product form. Okay? Right? Next, if a point, if the question gives you a plane, right, that passes through a point and containing a line, right, a line, okay? Now, in order to so-called identify a plane, right, either I give you 1 point and 2 direction vector, or I give you 1 point and a line, or I give you 3 points. Right, these are the 3 ways I can actually describe a plane. Right, so if you look at this figure here, right, the question says find the vector equation of the plane that passes through this point and contains this line, right? Now, notice that the direction vector of the line, right, is of course your first candidate of D1, isn't it? The direction vector is straight away the candidate for your direction vector of the plane. So where do I get the second direction vector? Right, that's where AB comes in. Right, so isn't AB also a direction vector of the plane? Right, because it passes, A and B are both on the plane, isn't it? So AB will then be a direction vector as well. Okay, so there we have it. We have these 2 direction vectors. Then I can construct the equation. Right, so under the thing zone, right, of course, we propose another equation, which we use B instead. Again, as I mentioned earlier, right, the equation of a plane is not unique when it comes to vector form. Right, it's not unique. Right, you can choose any point you like. You can choose any direction vectors you like, as long as they are parallel to the plane and the point is on the plane. Right, so it's not unique. Okay? Next, when I pass through 3 points, very simple. You can choose AB as one direction vector. Right, all I need, I can always use AB, right, as one of the direction vector. And AC, right, is another direction vector. Of course, I can use BC. Right, I can also use BC, it's fine. All right, so with that, in this case, let's just use AB and AC. So the vector equation is just OA plus lambda AB plus mu AC. Right, once again, this point is not unique. You can always use B or C instead. It doesn't really matter. Right, so once you understand the idea of this, again, as I said, I'm more interested in the scalar product form, right? Because normal is the one that is unique in the sense. Right, so that's your case 4. I give you a point and I give you the normal. Right, this is the best equation when it comes to planes. Right, and I already explained to you how I got this result, so I won't go through in detail. Now, okay, this is actually so-called the scalar product form. Again, right, this is actually the most useful form for the equation of a plane. Right, so I will always use this. And a very nice thing about this form, right, is that this number, there's actually a hidden meaning. There's actually a hidden meaning in this form. Remember that this number is actually a dot n. Right, so if I look at things from the side view, okay? If I look at things from the side view, if this is your plane, right, and this is point A, right, so remember that n is the normal. So isn't the perpendicular distance a dot n cap? Right, isn't the perpendicular distance a dot n cap? If you look at this diagram, this is the side view of the plane, right, with reference to the origin, right? So this distance here, right, remember this distance here, right, is actually so-called the adjacent, right, to this angle. And this is your angle between OA and the normal. Right, theta is actually the angle between OA and the normal. Right, so in some sense, you're actually projecting OA to the normal. And this actually gives you the perpendicular distance. Right, so when it comes to planes, which might be a bit confusing, in lines, right, cross product give you the perpendicular distance. Right, whereas for planes, dot product will give you the perpendicular distance because you're looking at the normal. Right, the normal is perpendicular to the plane. So the dot product will then give you the perpendicular distance. So in this case, right, the number d, right, has a very nice meaning behind. If I divide d by mod n, if I divide this number d, right, by mod n, it's actually the same as a dot n cap, which actually gives me the distance of the plane from the origin. Right? So this is a very useful thing you have to remember, that this number, r dot n equals to d, right? The number d kind of give you a meaning about the distance of the plane from the origin. But to get the correct distance, you have to divide by mod n. Okay? So the small d here, right? So let me just write down here. Right? So if your equation is r dot n equals to d, right? You must first convert to r dot n cap equals to d over mod n. Okay? So the perpendicular distance from origin, right, will then be mod d over mod n. Alright? So this number actually tells you how far away, right, the plane is from the origin. Right? And if this number equals to 0, I can conclude straight away that the plane contains the origin. Right? If this number is straight away 0, I can straight away conclude that origin must be on this plane because the distance is 0. Alright? Which is a side remark. Okay, over here. This is a remark. Right? If it contains the origin, then this number has to be 0. So r dot n equals to 0. Right? And furthermore, the sign of this number also gives you some idea about whether the plane is above the origin or below the origin. Let me just finish this off. Right? Whether is it positive or negative, right, actually tell me whether the plane is above or below the origin, in some sense, with reference to the normal. Alright? So this diagram here, right, shows you that if a dot n cap is positive, with reference to the normal, the plane is actually above the origin, right? And if a dot n cap is negative, the plane is actually below the origin, with reference to the normal. Using the normal, right, as the reference axis in a way. Okay? Right? So with that, have a good weekend. I see you next week. And don't forget that Friday you have your lecture test. Be prepared for it. All right? Hope to see a good showing from you.